Hello, and here we go. Welcome to another episode of Containers from the Couch. Today, I'm excited to invite guest speakers from NVIDIA to talk about building and customizing generative AI models running on Amazon EKS using a tool called NVIDIA NeMo. Right off the bat, let's go ahead and introduce our guests today. Nirmalya, who we've got on the couch. We'll start with you. Tell us a little bit about what you do at NVIDIA and what we're going to be talking about today.
Thank you, Shai, and thank you, everyone. We are excited to be here talking about NVIDIA NeMo. Sometimes I say that my job is finding Nemo, but basically I manage various NeMo LLM products, which includes framework, which includes NeMo community models, and which include NeMo managed service. So overall, my job is to focus on the product areas on Gen AI leveraging NeMo.
Awesome. And I got confused. I thought this was an episode talking about marine biology. Okay, good to know. Good to know. We're not talking about finding Nemo. NeMo, of course, standing for neural models. We'll dive into that a bit more. Wenhan, next, let's jump to you. You're going to be driving our demo today. Super excited to see how all of this works on Amazon EKS. Tell us a little bit about yourself, what you do at NVIDIA, and maybe give us a little sneak peek into what you plan on demoing today.
Yeah, hi. Thanks, Jai. Hi, everyone. I'm excited to be here. I'm Wenhan. I'm a solutions architect at NVIDIA for about 2 years. So we work with different customers that work with NVIDIA GPUs and models. And I'm here to present a small demo today along with Maria. We'll be presenting how do you customize a model before and after EKS using NVIDIA NeMo. Thanks, everyone.
Excellent. Well, thank you both for joining us today. Look, we're really excited to see how all of this works, but I think first we need to lay some groundwork of what are we exactly talking about today. At the very base of it, I think it's NeMo. And so Nirmalya, I want to start with you. Tell us a little bit about NVIDIA NeMo.
NeMo is a platform which enables you to create, customize, and deploy large language models and generative AI models. So you can think about, as Shai mentioned, NeMo stands for neural models. So as we see the overall landscape today, the LLM journey varies at different layers of different companies. So NeMo tries to cover all of the phases of the journey. If we can go to the slide, thank you. So if you think about where you can start your LLM journey, you can start your LLM journey at data curation. Anyone who is creating foundation model or even customization, data curation and data creation is the fundamental part of that process. We provide solutions for data curation. Then the companies who are really looking to create foundation models from scratch, NeMo is a very performant framework which enables you to create those foundation models. Some companies who like to take foundation models, Amazon Bedrock, Amazon Titan, right? One of those examples, and we provide tools. And when we talk about customization, there are various kinds of customization. One is fine tuning. You take a model and you do continuous training. Another kind of customization, which is very popular these days, is called instruction tuning. You do techniques like, RLHF, reinforcement learning with human feedback, or you do supervised fine tuning, or you do a technique called steer LM to steer the model. So we support all those techniques and we are constantly investing on those techniques. And finally, we find majority of the companies are doing PEFT, parameter efficient fine tuning customization like P-tuning, prompt tuning, LoRa, and those kinds of techniques. And we make sure to support all those techniques. So once again, on the training side of the things, data curation, foundation model training, continuous training, instruction tuning, and customization, we try to provide solutions at each phases of the LLM journey. And finally, once you are trained, you want to deploy the model. So definitely we provide a very performant and efficient solution for deployment. So that's overall, you can think about what NeMo covers at each phases of the LLM journey.
Okay, so that makes a lot of sense, and so we see this kind of as a journey. Now, foundation models themselves. I want to ask you to tell me a little bit about what is a foundation model, and does NeMo help you make foundation models themselves, or are we talking more about fine tuning them and deploying them?
Yeah, NeMo helps in both, right? Definitely, NeMo is, helps you create foundation model. And if I may, you can say we just wrote a blog with Amazon, and thanks to the Amazon team with Amazon Titan, we are very proud to work with them. They use 10,000 GPUs. You can look at the public blog for us, the very large foundation model Amazon trained with us. So that's one of great examples. We are very proud of that collective work. So that's what NeMo does. There are similar, globally, we do similar kind of work with Korea Telecom and other companies. Now, on the fine-tuning side, of course, we do provide fine-tuning. And there are companies who want to enter the LLM journey at different phases. Like Amazon, in this case, entered the LLM journey with NeMo at pre-training. So that means you have tremendous amount of data with trillions of tokens, and you start create a foundation model. And either the foundation model can be for specific tasks like software coding, or it can be kind of general purpose, as we call general intelligence. And now, so that's the foundation model. And on the customization side, also NeMo helps. Like you can take a foundation model and you feel like, okay, I want to do a domain-specific foundation model through continuous training, like what Bloomberg GPT did, right? So that's a finance domain. Or you can think about, no, I want to do a customization specific on a task. Like here is my task on a summarization on news article. I want to bias the model, condition the model to do that task. You can do techniques like prompt tuning, low ranking adaptation on LoRa, and so forth. We make sure our job is to provide you the best techniques which creates ease of use and the most accurate custom model.
Makes a lot of sense. So, Nirmal, you mentioned a lot of different types of use cases, industries that this can apply to. Now, of course, a lot of us are familiar with large language models that allow you to talk to them and get, insightful responses back. And then there's other types of models to help generate imagery. Now, are these both kind of the same types of foundational models, or are they different? And does NeMo really care about what type of models they are, or are they all kind of supported here?
Yeah, so a very good question. NVIDIA creates its own foundation model, like NVIDIA Nemotron 3.8b. You will find on Hugging Face, you will find on NGC, you will find publicly available. As well as we are investing quite a bit optimizing the available foundation model like Llama 2, like StarCoder 1, and those kind of foundation models we optimize through our framework, such that this is a very performant model, both through in its training and its inference time. So from our point of view, here is our vision. World's best Gen AI models are .NeMo model. By that, what I mean is, it has trained or optimized with NeMo framework. So answer to your question is, no, it does not matter. We try, either you can use our model or community model. We like you, the developers, to have the best experience in training, best performance during inference.
Okay. Now, that makes a lot of sense to me. And by the way, I just think it's so funny that we have to sit here with a straight face and talk about things like Hugging Face or Llama 2. I think the naming here is just awesome. One of the questions that I had here today, our demo is going to be showcasing NeMo running on Amazon EKS. But let's pare that down. Why would you want to use Kubernetes? Running your own infrastructure, managing your own cloud interface to run something like NeMo. What's the value in kind of defining all of those configurations?
Yeah. So what we'll say is, look, what we see from the, let's look at from application parlance, right? So the applications, what we see are more and more applications are running with Gen AI. And most of the application workload is during inference time, because you don't do training all the time. You train once and then you do periodic refresh or whatnot, but you really run inference to serve your workload. And during inference, you are supporting various models and you need to scale up. So basically, the amount of your workload coming to your inference time, you want to scale up. Kubernetes is the unique solution which helps you to auto scaling according to your need. So that's why we find, working on Kubernetes solution is really, really the right way to go for inferencing. And we found out working with EKS, as you will see on the demo with Wenhan, it was really easy and it was really, performant when we were able to scale up and scale down as the inference needs changed during the application time.
Absolutely. Another concern that comes to mind is data privacy. A lot of these companies that want to be able to feed in custom data, maybe sometimes they're geographically locked due to regulatory or compliance concerns. For a lot of these companies, privacy is critical. And so running on Amazon EKS with NeMo, can you talk a little bit about how we're addressing those types of use cases when privacy is a major concern?
Yeah. So definitely, we understand that data privacy, data ownership, and data fidelity is extremely important in the Gen AI ecosystem. So that's why NVIDIA's approach is very unique. If a customer wants to run on the cloud, on the private instance, what we can do is we can give you all the building blocks to create a LLM serving application. You can get our training container, you can get our inference container, and you can get our models. That's how we try to provide you a flexible choices such that you can control where your data goes, where your data resides, and how do you, enable the data. So that's what kind of fundamental approach from our side. You can use a hosted service, and I'm sure as we work with Amazon on EKS, AWS takes care of those data ownership. But from NVIDIA's approach, we provide you those modular components such that you can install and control your destiny. That's one piece. The second part of that is the framework itself provides you a lot of tools, lots of techniques, like once you do a training, right, you want to understand that, is this output toxic? Or is this output bias? Means I'm just a little bit taking your question to a little bit, that may be a follow-up question. So that is very important from our point of view, right? And we have to provide you the right kind of tools and information such that you can decide what is toxic for your application, what is bias for your geography. So we strive hard to provide that kind of techniques, scripts, and examples as part of the NeMo framework. So in summary, Shai, that, we provide the components, the modules, and we work with Amazon to build up that service layer. And definitely from the privacy point of view, we trust, Amazon's infrastructure to manage that. But, as we mentioned, we provide the modular components and we leave the destiny for the users to control by themselves.
Okay, excellent. So this all, I think, is a perfect lead up into the demo that we're going to be showing today. Now, the demo is called NeMo Megatron Launcher. Now, that's a pretty badass name, but what is it? What exactly are we talking about here? And I guess this is an open question to Wenhan or you, Nirmalya.
So, in fact, we have not done great job. We have to improve our naming. So NeMo Megatron is equivalent to NeMo Framework. Essentially, NeMo Framework Launcher is the whole package of NeMo Framework, if you think about. So the listeners, the viewers of this presentation, if you are listening to this, you get excited to NeMo, you will see NeMo Framework in action. And Shai will share, you can get access to the NeMo Framework applying through the link, which we'll share with you, and you will have access to our NeMo Framework containers. You will get training, and you will get inference container, and the demo what when will show it to you will be able to you will be able to access. At the same time, we take a very open approach to this creation of our products. So whatever is in the container, we also do it open source. That's what I mentioned, the GitHub link of NeMo Megatron launcher, and you can take the also our source code, and if you like to, you can create your own container, taking the checking out the source code from GitHub. So choice is yours. Definitely, we take a lot of care through our regular nightly testing, script, performance. That is very important in these cases, and make sure that you, the developers, get the best performance out of the NeMo pipeline.
Awesome. Okay, so we've been teasing the demo long enough. Wenhan, tell us a little bit about what you plan to demo, and just so I understand, the idea here is that running on EKS, we want to demonstrate NeMo customizing a model, right?
Yes. Are you able to share my screen real quick?
Yeah, got it.
Perfect. Okay, so we have let me do this in the present mode. Is it loading on your screen?
It's a black screen right now, but I don't know. If it's showing on yours, you might just want to show the view.
Yeah. Maybe I'll just do the preview.
Yeah, that looks good.
Okay, so for NeMo framework on EKS, NeMo framework already has Kubernetes implementation, but that was only supported on the local. And to make it work on EKS, users need to replace the original NFS file system with EFS. I'll talk about that in the demo later. But pretty much what you want to do on EKS is you launch an EKS cluster with GPUs, and you want to create an EFS file system on it. And after that, you want to install some of the operators to run your Kubernetes setup. And at the very, very end, you can just use NeMo framework to start a training job. And we have a quick example here. So today we're going to use a Llama 7B model. That's a foundation model from Meta. And we're going to give it a small task. We're going to ask a quick question about an FLT, and we'll give it a context. And as you guys can see that at the very end, before customization, the prediction is nothing. So the foundation model doesn't even understand what it's doing, because it's not being fine-tuned or being customized with a specific data set. And after you get customized with a specific data set, the model is able to understand the task, is able to see, okay, you're asking me a question, and I'm going to find the answer from the context, and I'm going to give out my prediction. And at the prediction here, you can see that the prediction is Denver, and it's the same as label. This is a quick snippet of the demo that I'm going to show today. But other than that, is there any other questions?
So that's the raw kind of before and after, and I know that you were showing me this before. You ran it through the actual model, and the actual output is in a CLI JSON file with hundreds of other outputs. So that makes a lot of sense. What's the model, by the way, that we're running this through?
The model is a Llama 7B model.
Got it. And so the idea is that beforehand it didn't know the answer, and then you run kind of this customization of the model with some custom set of data, and then when you ask it the question again, it now knows the answer. Okay, awesome. So I think that's helpful for us to kind of ground us in what is this actually doing. But let's jump into the technical pieces. I believe you have a demo for us showcasing how this runs on EKS, how this whole NeMo process will actually run.
Yeah, and before that, I want to quickly go over the blog. Sorry, not the blog. So the guide that we have written up for running everything for NeMo framework on EKS. And I'm going to go over to the blog now. And hopefully it's big enough on your screen. So in order to launch anything, for example, at the very first step, we're going to launch an EKS cluster. And to do that, you can do it on the web, but if you want to do it on your command line on your computer, you just need to install your AWS CLI. And to do that, we have already written out here. You will need to install your AWS CLI. And after that, you need to install your kubectl, your EKS CTL. And at the very end, your Helm command lines. Once you have all these ready, we'll go ahead and launch an EKS cluster. And to do that, you need to have your cluster YAML file ready right here. This is showing just as an example. So I'm going to have my name called Munhan/cluster, your region, your version number, but more importantly is how you want to set up your nodes. In today's demo, we're going to use an AMI from Ubuntu, and this Ubuntu is a specific AMI that works with NVIDIA GPU operator. That operator is able to let EKS cluster or any cluster, Kubernetes cluster, to gain GPU controls. And after that, you want to define what kind of instance you want to use on EC2. In this case, we're using G5.12 large. This instance has 4 810G NVIDIA GPUs, and each one is 24 gigabytes memory. And we want 2 of those instances. So we're doing 2 nodes, each node with 4 GPUs. And for volume size, this is just how much storage you want for each instance. I just set it to 200. You can change it to however large you want to. And the rest is pretty standard, just the bootstrap command you want to use, and also the SH key. After that, you just need to run a simple command with EKS CTL create cluster with the file name that you just created. And
so one hand, this is a pretty beefy cluster. That's 8 GPUs distributed across 2 nodes. So yep. I've got to ask you, what's the value of adding more GPUs or more compute for the training process?
Definitely. Yeah. So for we all know that for inference side, users tend not to. You don't really need too many GPUs or multi-node. It's not even like pretty much no one does multi-node on inference. But on training side, because of all the activation weights that you need to run and all these back propagation calculation you're doing, the number of GPUs that required to train a model is a lot larger than inference. And with more GPUs on it, you get more GPU memories, so that there are different kinds of parallelism that you can do. So with more GPUs on it, you can reduce the training time. You can improve your GPU utilization. You can split the model across GPUs, or you can split the data set across the GPUs, and or even with the latest sequence parallelism, you can parallelize your sequence, and all of that is a benefit from having more GPUs and multi-nodes.
Got it. And just in the world of being cost optimal and frugal, ideally you really only launch these nodes, these instances, this cluster when you need to run some training, and then you would scale that back down when you're done training it, right?
Yes.
Okay.
Yep.
Excellent. All right. Well, I think we're ready. Let's get into it. I know you pointed out one thing that you had to create an EFS file system. So there are considerations when running this on Amazon EKS as opposed to maybe like locally or in another environment, right?
Yeah. So when you run Kubernetes in NeMo framework, the original setup in our NeMo repo was to use an NFS file system. That's local. And in order to use it on EKS, we need a file system that's available to all the instances on EC2. And EFS is the way to do that. There is another option called EBS, but that does not support mounting on multiple instances, but EFS does. So we're going to use EFS today. And that will be shared by all the nodes that you created. And so that when training is done, or even in between trainings, when you're saving checkpoints, all the nodes have access to the same hard drive, so that's available to everyone. And you can mount it on as many instances as you want to.
Got it. Makes sense.
Okay, so should I just go over the demo now?
Yeah, let's see it.
Got it. Okay, so now we have EKS ready, And I have already created that beforehand. Let me show that to you. So on the web, okay, so on web, I have already created a EKS called 110-cluster. And in there, you can see how many, you can see the number of node groups that you have. For example, here we have 2 node groups, and this is the ME that I just mentioned with the GPU operator in there. And inside there, we have 2 nodes. Each node is G5.12x large, and they're all created already. And if you want to, you can see them on your terminal. You can see that we have created this on here. And this is the cluster, as we just mentioned, how to create it. And the next step is EFS. So go back to the guide that we have here. You want to create an EFS file system. It's really simple if you do it on the web, because it's just a few clicks away. But if you want to do them on your terminal, we have guides here, and you can. It's a pretty much standard steps they can just follow. And once you have created your EFS file system, you want to make sure you have your driver installed on your cluster. And because even though your EFS file system is created, your cluster does not have some kind of connection to your file system. And you want to make sure your driver has that control. And in order to do that, let's go back to our cluster. There is a add-ons. In add-ons, you can pretty much add this Amazon EFS DSI driver. This driver will allow your cluster to, like I said before, to get control of your EFS file system. And once you have this installed, this is a much more easy step. I can go through it quickly on the screen, but you want to go to add-ons, and in there is an option for Amazon EFS file system. And once you click that, I'm just clicking a random one here because I've already added in here. You would pretty much just go next and next. And after you're finished, you will see them running at the bottom, and you can check the status. And once it says it's active, then you're ready to go. And after you're done with your EFS file system, you can actually see them on web as well. So this is the file. Let me refresh.
So this is going to be a network attached storage, allowing us to connect, a common file system across multiple nodes, which is what the training model here needs, right? Okay.
Yep, exactly. And this is the file system that we have created before today's meeting, today's call. And we have in there, you can see how many, what the network of it is, it's mounted. For example, we have 2 nodes that's being created in our cluster. So we are going to mount them in US West 2A and the US West 2C. These 2 are the subnets that our nodes are being created in. And all of these will be provided in the more comprehensive step-by-step guide later. I'm skipping those miscellaneous steps just for today's purposes. But once you have done those, you should see them here. So that means your EFS file system can be available on this subnet and this subnet. And once you have done these, then you should be ready to go, because everything is ready and your EKS have access to your EFS file system. And you can go through the installing part. But before I do that, I can quickly share what we have already set up. So let me go to my workspace. Okay, so I am in a directory. That's where my EFS file system is mounted on this instance. In that instance, I have these 2 files in there. I'll go over these 2. And on the other instances, because EFS file system can be shared across multiple instances, you can see the same thing on a different instance, EC2 instance. In this case, let's go there.
So what I'm looking at here, you've SSH'd into both of those nodes, those G5 12x large instances.
Yep.
Okay, got it.
Yeah, So you can see that we are seeing the same thing on different instances. So that's good. That means the file system is set up ready. And we can go over to the next step. The next step is we need to install all these operators. We have step-by-step guide here. You don't need to worry about how to install the right version. But the most important part is the first one, the very first one, the GPU operator. You will need this for your job to run on GPUs. If you don't have these installed, even though you have GPUs in your cluster, your Kubernetes will not know how to use it. This is like the guide to tell Kubernetes how to control GPUs. And the rest is more for like the training purposes, like the kubeflow training operator. It allows NeMo to start a training job. And there are some customizations you need to make on it, but those should be fine. And at the very end, once you have all of these installed, you're able to see them in your Kubernetes control. Let me see if I can quickly show that. Okay, so first of all, we can see our two nodes are ready in our terminal. They're both ready, and let's see if our operators are running okay. Okay, I don't know if that's too big on your screen, but as you guys can see, we have the GPU operator ready, running, and we have the NVIDIA container toolkit running. Those are, you don't need to install this specifically on your hand. Those are coming along with the GPU operator. It's just one command line away. It will install all these automatically for you. But you just want to make sure that everything is running, and no errors coming up, then you're good to go. And at the end, you'll see, okay, we have those two nodes. That's for Kubernetes, for EKS purposes. And at the very end, we have the EFS controller that's running. These are all automatically installed for you once you add the EFS CSX controller on your cluster on the web. And we see that everything is running, then we're good to go. So now we come down to the NeMo part. Okay, this is where we're going to show the quick demo. So in this directory, we have a folder called NeMo Megatron Launcher. This launcher has all these files in there, and including how do you launch the EKS, including how do you launch Kubernetes, how do you launch a training job, how do you launch a fine-tuning job, and also how do you start an inference. And in here, we're going to see the specific script called main.py. And you can see this on the public free repo. It's all available there. And this main.py, what it does is that before you start a training job, you will need to use this script as a start button to start a training job. I'll show you that later. So if you want to use this script to start a training job, you simply does this, and it will start everything automatically for you. But before you do that, you want to make sure that you're running the right config. And there is a config file in this folder that tells NeMo what to do. And I'll show that quickly here. And this config file at the top, for example, you can specify, if you want to use Kubernetes, or if you want to use BCP, and some other cluster types. And if you want to, and for data preparation, what data set you want to use, what model you want to use. And same thing here for training, what kind of training model you want to use, how large you want to use. And for fine-tuning, for PEFT, all of these, you can set them up. And at the very end, there is a stage option. You just want to make sure that this is on the right stage. So this will control, this will tell NeMo, okay, what task it wants to execute for you. And so once you set these up correctly, you want to make sure, okay, now, for example, if I want to go do a PEFT training job, what specific details we want to control in PEFT? There's another config that controls that. So in the config folder, there's another one called PEFT. In there, today we're going to use Llama. And there's another YAML file in there. in this YAML file, this is where you specify, how large your model wants to run, how long you want it to run, the step size, the epochs, how many GPUs you want to run, what's the precision, and all that other data set related stuff. But inside there, you can see there are all these settings that you can do. I've already set this up correctly, so we can go ahead and launch the training job.
So Wenhan, real quick, I just want to point out, so up until now, setting up the EFS, the cluster, all of that, in an ideal world, there's a cluster operator that does all of those steps. Now that we've gotten into actually running the training jobs, I love the fact that it's wrapped, the YAML pushes, deployments, configuration is all wrapped into a Python script and some config files, because feasibly, the data scientist who's running the training, feeding them the data, is different than the person who's setting up the cluster and the operations behind the pie. So I like that you showed us both ends here, but it seems like the user experience for actually training the models is fairly straightforward. Run this Python script and edit these configuration YAMLs.
Yeah. Once you have your EKS, your EFS file system set up, like just a general Kubernetes cluster setup on AWS, everything else on the NeMo side is to change your config files and run this main.python script. That's literally all you need to do on the NeMo side. There are a specific changes that you need to make based on your cloud. For example, on Amazon EKS, we are using EFS. So we need to make changes on the file system setting in NeMo, and I'll show you quickly where that is. So same thing in this folder, we have a folder in NeMo Launcher. In there's another folder called Core. And inside there is a folder called Kubernetes Templates. And inside there, we can see there are 4 folders in there: conversion, evaluation, training, data preparation, and PFT. We're looking at PFT today because that's the one we're going to change. And inside the PFT, there is another file called PFT YAML file. This is Kubernetes manifest. This is where we want to modify the file system to use EFS. I've already done that, but let me quickly share with you guys what that is. If you look at line 51 and 52, you can see that I have already changed that to a persistent volume claim. And the claim is links directly to my EFS. And this is the only thing that you really need to change in there. Everything else is leaving default. And I also have the EFS written out ready as a persistent volume. Let me quickly show you what that is. Okay, and as you guys can see, I have persistent volume set up for EFS, and I set it just to give 200 gigabytes. That should be more than enough for the checkpoints, for the Llama 2 checkpoints. A single Llama 2 7B checkpoint takes only 25 gigabytes. So 200 is more than enough. And this is ready. Then that means our Kubernetes or our Helm charge has access to EFS now. And
Wenhan, earlier when you showed installing the EFS add-on, the CSI driver for EFS, that add-on is actually what's enabling us, Kubernetes rather, to recognize these persistent volumes, these persistent volume claims, and translate those into the API calls to create the actual EFS instance. So really changing the onus of creating EFS itself to a service, Kubernetes. These services can create the file systems on demand when they need it, which I think it's a good model for working with EFS. So in that configuration, you showed the persistent volume claim. Could you also show where we actually define the EFS, the mount path?
Oh, yes. So let me go back to that. So the mount path, it's also in here. So previously we were looking at line 51 and 52. That's where we tell, okay, this is the EFS claim. But where do we actually mount it is in line 40. This workspace directory is what we want to use. This workspace directly links directly to here. But this mount path, this path is what we set in the values folder. But I leave that in default in blank. So what it will does is that you will mount it in a backslash folder, meaning you will create the file, you'll mount it at the very root file directory. So this is where you control where you want to mount. You can change it to whatever you want. For example, you can name it to EKS directory if you want to, but this is where you change it.
Got it. Okay, Wenhan, I think we've spent a good amount of time talking about the operator side of the world. Let's go back to the data scientist side of the world. And I think, you know, we assume all of the tech stuff is set up. You know, we've got our model that we want to deploy. How does that look?
Okay, so everything is ready. We want to use the simple script to launch the training, and I'm gonna launch it for the demo purpose here, and you can see that it's running a few stuff, but it was through an error. It was saying that, okay, you cannot reuse a name because I already have that running, and let's see that it's actually running. Okay, so we can see that we already have these two running. I run it beforehand, but this is what you will get after you run that script. And you can also...
So just so I understand what I'm seeing here, so you kicked this off 155 minutes ago, so a little over, you know, 2 hours ago, and yep. 2.5 hours ago, and it's been running on both nodes for this entire time. Yep. What monstrosity are we training here? Like, how many data points are we working with?
We are using a data set called Squad. You can modify how long you want to change, how long you want to run it, but usually you want to look at the training loss graph to see, okay, is it training well? But I won't be showing that today. I can show that today if there's time available. But typically for Squad data set and also for Llama 2, you would take about 3 to 4 hours, and on 810G GPUs to finish. It also depends on the settings you did in the config file. There are different settings that you can do to make your training more efficient, and you can probably reduce time to like 3 hours to 2 hours down. Yeah, but those are available in NeMo.
So I've got to ask. I mean, there's obviously a optimization path here for defining, do you want a cheap GPU node running for 24 hours, or do you want 10 of the biggest, best worker nodes, you know, the P5 instances with the new H200 GPUs, I believe, running for 30 minutes? I mean, how do we help our customers determine what's the best cost optimized route for training or deploying one of these models?
Yeah. If you want to if you want to save the last time, say, for example, if you already have something that's working and you know you already have the best training optimal, you want to try to use as many GPUs as possible. But if you have a single GPU, for example, A100 or H100 from NVIDIA, they are already more powerful than probably 4 810Gs. So if you can use that, then you probably don't need 4 810Gs. You can use just a single A100. That's already much more performant than 4 GPUs running together. So there are different use cases, and depends on different use cases, users need to test it to find the best setup for them. But generally, the general rule is that you want to try to use the best available GPUs available.
Is there a max number of GPUs at which point you get diminishing returns of efficiency? Like, what if we ran this across 100 GPUs? Like, is there a level where you start seeing it fall off?
Yes, definitely. If you run on 100 GPUs, that means there is a huge GPU to GPU connection, a communication overlap. If your model is really small, then you probably don't need that many, and the GPU connection probably takes longer than the actual training time. So there is a balance where you can decide how many GPUs you want to use. But the general rule is depends on your model size. For example, for Llama 7B, it would take, in our case, we're using 810Gs, but I'm pretty sure the GPU memory is not being fully used in there. And I can quickly check that just right now.
Yeah, I'd love to see, analytics, or you mentioned the tool as well, to see how the training is running, the GPU utilization here. I know you've already got it running, so it would be cool to see what that looks like.
Yep. Let me quickly go to let me try to find the command line I want to use. Okay. So we have these pods, like 1,500 minutes already, and we want to go to one of them to see how it's doing on the GPUs.
Could you move that sharing your screen window just out of the way a little bit?
Are you able to see that?
Yeah, there you go.
Got it.
Thank
Okay.
you. Yep.
All right, so we have just SSH into one of our worker pod, and inside there, we can do a command line called NVIDIA SMI. This is probably too hard to. Let me rerun it, and we can see that all GPUs, all A10G GPUs, are running at 100% GPU utilization on the right. But if you look in the middle here, the GPU memory usage is not being fully utilized. We have 23 gigabytes on one GPU, but we're only using 17 of it. So there are about 5 gigabytes being left on one GPU, and for 8 GPUs, that's a total of 40 gigabytes being wasted. So depends on your model size. You can reduce. In this case, I can probably run this in only like 6 GPUs. That's probably good enough. But usually you want it to be multiplied of 4. So people don't pick 3 or 7. You should pick like 4, 8, 6, 16. So in this case, if A10G is not available, there are other GPUs that has less GPU memory and it's probably cheaper than A10G, and that's good enough for your model. So you want to check your GPU utilization here. In our case, we have 4 gigabytes left for each one. But that's the general rule. You want to test it before you actually start training for a super long time. What people does usually is to let it run for like 10 minutes and just to see if everything is working. If not, they'll kill the job and try some other setup.
Got it. So at the end of the day, it's a lot of trial and error, and finding the perfect level of GPUs depends on the type of model you're using, the type of training data you're passing in, so on and so forth. So we're probably not going to sit here on this live stream long enough for the entire model to finish training. So can you show us what it would look like, or what the final output would look like once the model is done training? Like what's next? Do we deploy the thing? What do you do with it?
Yeah, so after your finished trainings, NeMo creates a folder called results, just right here. And inside that results file, we have all these columns in there. And there's another folder called results. In there, we have the log outputs, the TensorFlow, the TensorBoard events file, and also the checkpoints that we just saved. Let's quickly go to the checkpoints. In there, because we're using 8 GPUs, for each GPU, there's a checkpoint for it. And if you want, there is a .NeMo file. This is the file that's being outputted from the PFT training. And we want to use this .NeMo file along with the base model file that the base Llama 270 to run a inference test. And I have already run that beforehand. So we can quickly go to the results. And the results, let's go back to the previous slide. This is what we have before customization. Then before you train, model doesn't really know what the prediction output is. It doesn't even understand what the task is. But once you run it for like 2 or 3 hours, the model does know, okay, you're asking me a question. Now I'm throwing an answer from the context that's being given. And there are a lot of other tasks being done. The question that I put up here is just one small sample. The actual outputs from the demo is we have about 10K questions being tested for the training model. And in each one, you can see the input is the question.
So this is for testing it. For the actual customization, what data are we providing? Or am I getting that confused? Is it the same for the data to actually train the model to customize it? Are we providing these pairs of input questions and answers?
Yep, it does. Yeah. So this is just a testing set. For the data training, it will be a different set, but the format is the same.
Okay, and that training set, do you happen to have it handy? Like, what would that training set itself look like? Are we cheating here? Are we just saying the answer to this question is Denver Broncos, or are we actually, giving it in a format which it's extracting and learning from it?
Yeah. Let me quickly show you. So the data set is in here. This is the data set that's being used. So we can see that there are two prefixes. One is delf, this is the testing set that we use, and the other one is the training data set that we use. And you want to specify this in your config files that we just showed earlier. But you can see, but let me quickly show you guys what's actually in those files. I'm gonna pick train.
Dude, one hand, after this live stream, I'm gonna have you turn those sounds off in Windows.
Was that loud? Sorry.
No, it's just funny. It's one of the first things I do on any Windows machine. I go into the Windows and I say turn off all the alerts. But no, it's
yeah. Okay. I'm just gonna do it by hand. Okay. So that we don't. Okay. Oh, that's okay. I don't know if you guys can see on my screen, but it's printing out all the questions with answers and outputs. Is that clear?
Yeah, so this is the test set, right? So this is the test set that we're running against the model, and you do it before and after the training.
Yes, right. And yep. And same thing for the other one. There's a del right here, but this is the same format, just different questions and answers. Yeah. Okay. And then this is the actual output results that we tested before the model was trained on the left and after model is trained on the right. And you can see that as the first answer. This text is probably too small. Let me see if I can make it bigger. Okay, this is probably better. You can see that on the left before training, the model doesn't even know what's going on. It outputs nothing. But after you get trained, the model does know, okay, you're asking a question, and it gave you an answer from text. And we do this kind of test for 100 questions at the bottom. I'm just showing you the very first one as an example. But that pretty much covers today's demo. And to a summary, you just need to create your EFS, your EKS cluster, and on NeMo side, you just need to make sure your config files are ready, and you just run the simple Python 3 main.py script. Then you should be able to see them running on your EKS cluster, just like I did here. And let's see if they're still running. So, okay, sometimes you will get this because your AWS configure runs out of time and you just need to log into it. But it should be good. I think that covers the most of the demo today.
Yeah, Wenhan, you're SSH'd into the node itself right now, right? So I think if you have it configured on your local machine, you might be able to run that command. But that's fine. That's neither here nor there. I think this was a really cool demo. What we saw was NeMo allowing us to at least one part of what NeMo allows us to do is customize a large language model. In this case, we saw how the output before and after the training was different, and of course the applications of this are widespread, not just for language models like we saw today, but even image models and generative models that are out there. I think in one of our previous Containers from the Couch episodes, we trained a stable diffusion model with a specific pet. And then we were able to generate images with that one pet. We all know how hard it can be to get a family photo with your dogs. That could be an interesting use case or something like that. So we have a few more minutes here for our folks that are watching along. please drop any questions that you have. Wenhan, I knew we would get this question. The Google Docs that you were showing, the tutorial, when is it planned to be published? And can you share some details around that?
So we can,
yes.
I can share that. We have part of the documentation already available. The Kubernetes implementation in our regular documentation. We can link that, the framework documentation link, and definitely we plan to publish this whole as after this. But one thing I just want to, in conclusion of the demo, what I just like to mention for our audience is what you just saw is almost NeMo in full. You saw, yeah, let's go to that slide. In fact, what we showed it to, the core techniques of parallelism. You mentioned tensor parallelism, pipeline parallelism, and sequence parallelism. You saw that. You saw a technique called customization. And in this particular case, we use LoRa, low-ranking adaptation. And you also saw inference. So basically, you saw the whole end-to-end NeMo pipeline. And lastly, what I want to mention, what Wenhan was mentioning, you can control the, your time duration. One of the techniques you can mention how many epochs we want to train. And basically, you're looking at the validation loss and training loss curves. And if those are converging, then you can always manage your training time depending on what you are trying to, where you are trying to go. So we provide, in a nutshell, we provide all these techniques and parameters for you to efficiently train and deploy, and you saw that in action.
This is awesome. So folks, I just have to thank you so much for coming on the show and talking through this, because we're talking about such important use cases here, things that even 2, 3, 4 years ago were extremely challenging to do. But we're showcasing how now with tools like NeMo, we're bringing the ability to not only work with foundational models, but train and customize them, and to do so in a way where individuals or teams can do it on their own. I think it's really the power of what we're seeing here today. With that, just a couple minutes left here. Anything exciting on the roadmap for NeMo that you want to share here, Nirmalya? Anything even for how folks can get connected?
Yeah, I think you touched upon, we see the future of multimodal. And NeMo framework is evolving. It has already multimodal flavor. We support lots of architectures like Stable Diffusion XL. We support like Cosmos 2. We support newer and newer architecture. We do see the world in where it's truly multimodal, and text to video, text to motion, text to animation, and not only the foundation model training, also, as you mentioned, the customization of those models, meaning how do you customize? So the techniques like instruct picks to picks, dream booth. So those kind of techniques, as you will see, and from 2 years out, 3 years out, probably we see that, you are building, all of us building multimodal model, and that can, whatever the modality you are trying to input and whatever the modality you are trying to output will be much more seamless. That's where we are going, and that's where we are very excited about.
Well said, Nirmalya. All right, folks that are watching from home, thanks for tuning in. Be sure to follow us on twitch.tv/AWS or on YouTube. Subscribe to us on Containers from the Couch on YouTube. Thanks again so much to our guests, our NVIDIA experts here today that showed us how NeMo worked and even demoed it for us. Until next time, we'll catch you later.
Thank you all.
Thank you.